Last class we started learning about glaciers. Recall that there are two rules for a chunk of ice to be called a glacier. One rule is that the glacier forms from snow buildup. More snow falls every winter, then melts in the summer, and over time that causes a progressive buildup of more and more snow. The snow layers get so thick that they're very, very heavy and compress the lower snow layers into ice. As the thickness of the mass of snow and ice grows even more, the thickness of the ice increases because the pressure increases. Over many years, the ice gets thicker and thicker, and the sheet overall gets larger and larger and heavier and heavier. Now, how big and heavy does the ice sheet need to be before it's called a glacier? Well, there isn't any exact amount of ice or specific weight that the ice mass has to reach before it's called a glacier. But for most glaciers, a solid ice mass isn't reached until it's about 160 feet thick. For perspective on how thick 160 feet is, this is a glacier from Svalbard, Norway, and if I put a 6-foot tall stickman in right here, this is how tall he'd be compared to this 160-foot glacier. So 160 feet of ice is a lot of ice, and that's usually the thinnest that the ice can be before it's large enough to compress all the snow layers into a sheet of ice and be called a glacier. The largest glacier in the world is on this continent. Can you tell from the satellite photo which continent this is? It's Antarctica, which remember is a continent at the southern part of the globe. Except for a few places where some ice melts down to the ground in the summer, the entire continent is covered with ice, with glaciers, and on average the ice is more than 1 mile thick. Lambert Glacier is right here, and it's the largest glacier on Earth. It's more than 60 miles wide, 270 miles long, and its ice is about 1.5 miles thick. And when you consider all of the fresh water that's frozen into the glaciers on Antarctica, it amounts to about 70% of the fresh water on the entire world being frozen as ice on top of the crust of Antarctica in the glaciers. Now, the second property of a glacier is that it's so large that its own weight causes it to move. At first, geologists weren't sure that glaciers moved, but since the mid-1800s, it's been proven they move, and now with improved technology, GPS, satellites, and things like that, we can actually watch them move. Here's Crater Glacier in Washington State, and watch as it moves from right to left over this time lapse from 2005 to 2010. Glaciers move at different rates, though. Sometimes they move pretty fast, for a glacier, and other times they move slowly for a glacier. Sometimes, as we can see from this video, the same glacier moves faster at certain times and slower at others. Let's go back to the satellite picture of the Lambert Glacier, and I'll superimpose this image over it, which shows the speed at which various portions of the glacier move. So, you can see that even different parts of the same glacier move at different speeds. In this color-coded image, the red corresponds to movement of 4,000 feet per year, which is about 11 feet per day. The purplish pink is about 3,200 feet per year, or 8 3/4 feet per day. The blue areas are a speed of 1,640 feet per year, which is 4.5 feet per day. The green color represents glacier movement of about 800 feet per year, or a little over 2 feet per day, and the brown is about 160 feet per year, or about 1/2 foot per day. Now, I don't expect that you'd memorize these speeds. I only provide them to be complete, as well as to give you some idea of how fast glaciers can move. When people are doing their work really slowly, sometimes a boss might remark that they are moving at a glacial pace, but when I think about hundreds of millions of tons of ice moving past me at 11 feet per day, I think that seems pretty fast. And the fastest moving glacier as of the time of this video is a Jakobsvand Glacier in Greenland, and it moves about 110 feet per day, which is more than 4 feet per hour, so you'd definitely be able to see it moving past you if you sat and watched it for a while. I'm going to run this time lapse again because I think it helps to drive home that these huge masses of ice actually move, and when they do, they're like huge bulldozers pushing, scraping, lifting, and moving massive amounts of dirt and rock as they scrape along the crust. Since glaciers cover so much of the Earth's surface and they move so much rock and soil from one place to another, like water and wind, they are an important cause of erosion, which we'll learn more about in upcoming classes.